I'll try to show you some sample problem solution for linear density and planar density. In the lesson, we have seen some numerical values are possible to find for linear density and planar density, like per nanometer or per nanometer square. Now we will have somehow different examples. So in this question, for example, the linear density is being asked for the certain direction in the BCC crystal structure. To answer the question, first we need to figure out which direction we are talking about. So let's try to plot the direction first. We are given the XYZ values as 0, -1, and 0. And if we try to plot them, X, Y, and Z, X and Z are 0, Y is -1, so it should be somehow in this direction. Let's put the -1 here. So our vector should be like this. We can try to plot it on the crystal structure as well. So let me draw it first. It will be something like this. Okay, if you like, you can also plot the axis like we did for. So the axis will be this X, Y, Z, and our direction will be like this. So normally the linear density was defined as the number of atoms per unit length of the direction vector. Let's try to proceed with that definition. So first we need to find the number of atoms on the unit length of the direction vector. When we check which atoms are on the vector, in fact, that one and that one. But only half of the atoms are covered by the vector, so it should be 1/2 of an atom times there are 2 atoms. So the number of atoms is 1 atom on the unit vector. Okay, so we need to find the length of the unit vector here. And since we are not given any R value or A value, we will try to write everything in R parameter. So let's try to find out the length of the direction vector in terms of R. To find out that value, first we should remember that the length for one side of the cube is equal to A. And for that specific geometry, I can plot the vector also here. So it will be like this. And to see it better, I'm just drawing it on the front face as well. So it will be like this. And now we know that the length of the unit vector is A, is equal to A. But I will try to relate it with the R, because I need to write everything in R in terms of canceling the units to find out some linear density value, because I'm not given any numeric value like nanometer for the radius or diameter of the atom. Okay, so how can I relate the A with the R for BCC crystal structure? To answer that, I need to know at which certain points the atoms are touching to each other. And for this geometry, the atoms are touching to each other on the space diagonal. So I'm just plotting the space diagonal now. On this diagonal, they're touching to each other. So the atom here on this corner, this atom is touching to the central atom, and central atom is in touch with this atom on the corner on the space diagonal. So they are touching to each other at those points. And when we check the distance for that space diagonal, I have R here, 2R for the central atom and 1R for the atom at the corner. So the total distance is equal to 4R. And that is space diagonal, and space diagonal is equal to square root of 3 times, not x, but a this time. So it's equal to a times square root of 3. A was the length for one side of the cube, as you may remember. So I found the relationship between the R and A. And let's try to write the linear density now. It was number of atoms per unit length of the direction vector. And the unit was somehow nanometer to the power of -1. But for that specific question, we will evolve it into somehow different way. Since we are not given any numerical value, as I told you before, we will be writing everything in the R parameter. So when we check the length of the vector, we should consider which portion of the length is covered by the atoms to answer the question. So in the unit vector, as you can see, we have 2 atoms. So this one and this one, but their hulls are in the plane. So we have 1 atom. And the length covered by 1 atom is equal to 2 R's, so 1 diameter. So this is the area, this is the length covered by the atoms on that direction. And what is the whole length of that direction? It is A. And how can I write A in terms of R? I can use that equation. So it will be 4R divided by square root of 3. So I'm writing it here. 4R divided by square root of 3. So we can cancel R's, and the result will be 0.866. So be careful, that is a unitless linear density parameter. So we calculate the linear density without any unit by just canceling out the R values. So if we were given the radius of the atom, or one side of the cube could be given to us, then we could go and find a value with some units. So it will be that many of atoms per nanometer. But since we are not given any numerical value, we just approach the problem in a different way. We calculated the length covered by the atoms. Over the whole length. of the vector. That ratio gave us the linear density for that specific direction in that specific crystal structure. Okay. I'm moving to another question about the planar density this time. So we are being asked about the planar density in FCC crystal structure for 101 plane. First, we again should try to find out which plane it is. So I'm just writing x, y, z values like 1, 0, 1. I should take the reciprocals of these values as 1 over 1, 1 over 0, 1 over 1 to find out the intercepts. Reciprocal. So the intercept values will be 1, eternity 1, which means the plane will be intercepting with the axis x, y, and z at 1. No interception with y because it's eternity. It will intercept at eternity. For z, it's again 1. I just put them on. And how will I plot the plane? My plane will be intercepting these two axes, but not intercepting y, so it should be parallel to y. So it should be like this. The plane will be this one. Okay, so we found our plane. Now let's try to transfer it to our unit cell. I will try to plot it on the figures here too. So it will be like this. You can also imagine the axis. So the plane will be this one. How about here? Let's try to plot it here too. So y, x, and z, the plane will be something like this. We change the color. So our plane will be this one. Okay, now let's try to find which atoms are in the plane. We will start with the atoms at the corners. So this one, this one, this one, and this one are in the plane, but not as a whole atom. Only the 1/4 of these atoms are in the plane. So let's write this number of atoms in the plane. So for the atoms at the corners, it will be 1 over 4. There are 4 atoms, so I multiply it with 4. Okay, how about the other atoms? Are there more atoms in the plane? In fact, there are that one and that one. So these 2 atoms are also partially in the plane. So halves of them are in the plane. So I'm writing 1 over 2. And there are 2 atoms. So it will give us 1 plus 1. In total, 2 atoms are in the plane. Okay, so I'm trying to find the density of atoms in certain area. So I need to find out the area of the plane. To find the area of the plane, I need to multiply that length with this length. So A and B, let's say. So the A is equal to the length of one side of the cube. We can keep it as A. How about B? Here B is equal to the face diagonal of the cube, so it will be equal to A times square root of 2. And that will give me the area. But as we discussed, we need to write the results in terms of R. So I need a relationship between A, the length of one side of the cube, with the R. And to find out that, I need to check at which points the atoms are in touch with each other for this specific crystal structure. And I'm just showing you the touching points for FCC for the atoms are these points. So on that line, on that face diagonal, the atoms are in contact with each other. That distance is composed of R to R, R. The total distance is 4R, which is equal to face diagonal of the cube. So if this is A, that distance will be A times square root of 2. So I have written the relationship between R and A, which I can use in the area calculation. So it will be 4R divided by square root of 2 times 4R, which will give us 16 divided by square root of 2R squared. So this is the area of the plane. And the planar density is the area covered by atoms over the whole area. We can also define it like that. And how many atoms are present in the plane area? There are 2 atoms. And area for one atom is equal to PR squared. That was for one atom. And since we have 2 atoms, it will be multiplied with 2. So we can write a planar density, a unitless planar density this time. The area covered by atoms over the whole area, which is 16 over square root of 2 times R squared. The whole area of the plane. The R's will again be cancelled, so we will find the value of that much, which is a unitless planar density. But if you were given some numerical values like R is equal to that much nanometer or A is equal to that much nanometer, we will be able to calculate the planar density something over nanometer square. So we could find the number of atoms per nanometer square. But since we are not given any numerical value for R or A, we just made our calculations for planar density by using the parameters we are given or we just know, which is R. So we write the area of the atoms and we divide it with the whole area to find out the planar density, which is unitless this time as that much. So if you have any questions, you can write me an email and ask about your questions. So have a nice day.